By theory, two sine waves plotted against each other create an ellipse. Depending on the amplitude and phase of those two sine waves, of course, they can also create a circle, such as the one shown on the animation on the screen. The orbit analysis relates the displacement measured over a pair of probes, each probe measuring its own sinusoidal wave, to angle of rotation, so it essentially measures the rotor movement. Such analysis is primarily used on turbines, compressors, pumps, and other typically but not necessarily large machinery. From rotor movement, different phenomena of lubrication and bearing states can be concluded, and consequently, operation can be improved and optimized. In order to measure orbit analysis on a bearing, you would need the following equipment. A frequency source that will typically be a key phaser with a single pulse per revolution. So this can be either a third proximity probe, which will measure analog signals, or it can be a digital tacho, or practically any other frequency source. Important to say is that typically analog or digital single pulse tacho is utilized in such applications. So besides frequency source, we need to use a pair of displacement transducers. Typically, those are proximity probes, and they need to be mounted at a known angle to each other, and of course to the key phaser. Mono configuration is also supported in our software, but those are fairly rare in reality. So those transducers are then taken to the data acquisition, which can be normally LV inputs, so such as the device that's shown on the screen, series 8 times LV, or if you use a digital tacho, for example, it can be a series 6 times LV, 2 times LV plus. The position of the probes and the key phasers are along the bearing as shown on the sketch. So let's touch briefly the background of our development and how exactly was orbit analysis developed. So our idea was to reimagine the orbit analysis measurement in a Dewesoft way. This means that we offer fully fledged turbomachinery analysis with signature easy setup and of course unmatched expandability that our software and systems are normally renowned for. We have taken the order tracking module, our tried and tested solution that's been used for many years around the world, and evolved it into an entirely new solution. And what are some of the key features that we can offer to our customers? The first and most important thing is the powerful analysis. So when it comes to orbit analysis, we offer a complete set of displays and functionalities for turbomachinery measurements. This means all of the typical parameters such as the direct orbit, averaged orbit, filtered orbits, subharmonic orbits, including shaft center line and typical displays that has been used in industry for years, such as the full motion graph, polar plot, body plot, to list just a few. Another important feature of our software is, of course, easy setup. This is also true for orbit analysis. So we developed our solution with the engineer in mind and trying to design it as simple to use as possible. Important thing is to be able to post-process the data. So if you only require raw signals, you can calculate the entire set of orbit analysis outputs also in the analysis mode. And we support the easily definition of the machine train. Machine train means that there is a number of multiple bearings measured along a single machine. And where do we stand out? So one thing that we can do is, of course, multifunctionality. So we can use orbit analysis with any other Dewesoft module and simultaneously acquire additional parameters, all data always synced. We offer high acquisition rates, which are especially useful for smaller rotating machinery that uses perhaps air bearings, for example, and we can offer monitoring capabilities. So this is handled in a case-by-case approach, and by doing this, we ensure that the customer gets exactly what they want. So we can couple orbit analysis with Historian and OPCOA. Of course, we don't have any hidden fees. This is always true when it comes to Dewesoft, and you always get the powerful DewesoftX software together with any dedicated analysis tool that you purchase. Okay, so now I would suggest we go into the Dewesoft software, where I will show how orbit analysis is set up, how do we define the inputs, and what outputs we can get. Okay, so as with any other plugin or basically any measurement we do, we need to first configure the analog inputs. First, we need to configure the inputs. So I've already taken the liberty to rename the channels that connect probe Y and X and also the key phaser. So next thing to do, of course, is we need to select the physical quantity. So in our case, this is going to be displacement or distance because we are using proximity probes, of course. The units will be set to millimeters. And then the scaling is typically read from the data sheet of the sensor itself. So I don't know the particular sensors that were used for the measurement, so I will set a scaling that is going to allow us to not get any overload warnings in the software. So I will set 1.2 for scaling of the both proximity probes, and I will use 2 for the key phaser signal. So besides setting these parameters here, of course, I can also go into setup to have additional settings at my disposal. And I can input here the scale or sensitivity. Typically, this will be sensitivity because it can be just copied from the papers that are received together with the transducer. As far as the analog inputs go, this is all we need to do. So afterwards, we need to add the orbit analysis module. So orbit analysis module is an option. This means that it comes together with the core installer of DewesoftX. Of course, it requires a separate license, but it does not require adding this in options. So if you click the More button, you will already be able to see orbit analysis under Machinery Diagnostics tools. So after opening the orbit analysis channel setup, we see a dedicated set of settings. To some of you that have perhaps used order tracking in the past, this might look fairly familiar. And that's because we try to keep the general idea as close to the one used in order tracking as possible. So first, we need to assign the inputs. We will start by selecting the frequency channel. So I am using the data from the third proximity probe, so this is analog signal in nature. So I need to select analog pulses and then Tahoe analog. So under the channel, I assign the key phaser that I've already renamed previously in the analog input to make the later setup easier. Once I open the section, the 3 dots settings option, I access the angle sensor mat setup directly. So here I can configure settings such as the trigger or rearm level, and maybe also define the lower frequency limit, etc. So for my particular case, 1.25 or 2.7 actually is going to be a suitable trigger level. Otherwise, we can always use the option to find the trigger automatically. Okay, so this is all that needs to be done as far as the frequency channel setup is concerned. Then we will move on to the RPM setup. So here, this is very similar to the settings in order tracking. We can define different test directions, meaning we can either select to do only Runout or only Coastdown, or to do both. Actually, if we select both, the system creates a third machine operation state that is called steady state. So for our data that we are using today, both Runout, Coastdown, and steady state were all done. So the direction setting is correct to use both. Next, we need to define delta RPM. Delta RPM defines the update interval for all of the outputs in orbit analysis. Meaning for 50 delta RPM, for example, each time the frequency source detects a change of 50 RPM or more, it updates the data in orbit analysis. Next are the lower and upper RPM limits. So these define the ranges of the calculation. For our particular case, the test is taking place between 300 and 3,500 RPMs. So I need to set the upper RPM limit high enough to capture all of the measured range. And these limits, they also define the range of calculation. So they make sure that the software behind correctly configures the resampling algorithm, which is depending on those limits and also depending on the max order to analyze. Okay, RPM setup is done. So moving on to the calculation setup. First, under the calculation setup is the harmonic list. So this is actually, again, the same as with order tracking. The user has the ability to define any harmonics that they want to extract. So for each harmonic on the list, the software will extract a corresponding filtered orbit. So another name for filtered orbit that might be more intuitive is also the harmonic orbit. Next in line is the order resolution. So this defines the number of steps on the order waterfall between the individual orders. The higher the resolution, the higher the number of steps between individual orders on the order waterfall. And this influences another thing. So the order resolution defines also the number of revolutions I need to have to get one block of data. So for example, 1/8 of an order resolution means that I will need to have 8 resolutions measured for one block of data. Next in line is the max order to analyze. So this defines the needed sample rate of the measurement and is of course heavily linked to the particular application that we are trying to cover. For example, if we use 32 as the max order to analyze, to calculate what is the needed sample rate, we need to take into account the upper RPM limit and also the Nyquist criteria. So the calculation actually goes as follows. Upper RPM limit in hertz, which in our case is 60, times the max order of analyze is 32, times 2 for the Nyquist criteria. So for the particular settings that we are using today, a sample rate of approximately 4,000 hertz needs to be used. The FFT window settings is self-explanatory. This essentially defines the window that is used on the FFT calculation. The user can select any window they want in the drop-down. Followed by the amplitude setting. So the amplitude setting defines what is the output amplitude of the outputs in orbit analysis, such as the Bode plot and polar plot. So we can choose peak, peak to peak, or RMS, depending on what we want to analyze amongst our data. Then we have the ability to define frequency axis unit in either hertz or RPM. You will notice that the RPM is here called CPM. So this actually means cycles per minute. So this is in order to create less confusions on the 3D graph. So typically if we select, for example, here RPM or CPM, then in FFT waterfall versus RPM, we will have two axes that will display RPM. So then one is called CPM to be able to distinguish between the two. This is just something normally used in the industry for such representations. The next section is fairly important. These are the update intervals for the data in orbit analysis. So we have the ability to update data on RPM change. So this delta RPM directly connects to the delta RPM set under the RPM setup. And then we have the ability to also update on time. So we can use either of the two criteria, or we can use both at the same time. On time means that whenever the RPM change is going to be smaller than the defined delta RPM, the update on time criteria will take action. You can see that according to the update on time criteria, the system also adapts the time for which the current center buffer size will suffice. The buffer size is the parameter that defines the number of shaft centerline points that can be stored inside. So for example, if I want to update every 2 minutes, then my current buffer size, which can also be increased, will suffice for 4 days. If I prolong this to 20 minutes, you will see that we can measure now for 40 days and so on. So the longer the time interval between individual updates, the longer the time that we can cover with the same center buffer size. And then below the update interval criteria, I have the ability to easily switch on order waterfall versus RPM and FFT waterfall versus RPM. So nothing special here. And then we are moving on to a very typical set of settings for orbit analysis. So one very important functionality of the orbit analysis module is the ability to perform runout compensation. So some of the competition call this also slow roll compensation, if you might have heard this before. This essentially allows the system to measure and compensate for the shaft irregularities. So typically this is done at a very low speed so that the shaft is not moving around. Instead, it's rotating steadily, and we can capture the irregularities in diameter of the shaft. So they can be compensated, and then later on we make sure to just capture the movement of the shaft without the irregularities in the shape. Another an important thing to point out here is that runout compensation, which I will explain briefly later, is excluded from the DC compensation, is excluded from the runout compensation. So the DC compensation actually compensates for the zeroth harmonic and is toggled in the following section of the settings. So let me come back to that later. The runout compensation itself can be done at the user-defined speed. So this is because some of the compressors that we currently measure on, our customers measure on, they can be positioned vertically. So this means that the runout needs to be done at a much higher speed than 200 RPMs. So actually this speed that you input here is only approximate. The system will be able to compensate up to twice the speed that you defined here. So for example, if I input 200, or I will use now 2000, I can successfully perform the compensation to up to twice this RPM value, meaning 4000. The averages input field defines how many averages I want to take into the compensation. 10 means that 10 revolutions will be taken then into one set of data. And the resolution defines the number of points along the single revolution. So 1 degree means 360 points around one revolution. And that's all there is so far as the compensation settings are concerned. Next, and very similar, is the reference orbit. Similar, it's because it's captured in a similar way. So here we have the ability to capture something that we call reference orbit during the measurement. So this is a reference of a current operating state. We have the ability to store this in the setup, and then in the next measurement, I can have this reference orbit in the setup, and I can compare on the same graph the conditions that were in the previous run to the current run. So this is very useful in R&D applications where you do modifications to the machine, and then you want to easily compare how the machine operated before and how it does now after the modification. So the averages setting, same as with the runout, just defines how many revolutions are taken into one set of data for the reference orbit. Moving on to the machine configuration. So this is now, I would say, the core of the setting for orbit analysis. So under machine configuration, I have the ability to create machine trains. So this was mentioned before on our slides. Machine trains actually just means more than one bearing on a single machine. So I can add them with the plus button, or I can easily remove them with the minus button, of course. Our particular data set only used a set of probes on a single bearing, so I will just define one bearing today. First, we need to assign the right channel to the right input field. So for Y position, I am using the Y probe that was renamed in the analog input to make the configuration easier. So I would suggest once you connect the transducers to your series slice, you rename them already in the analog input to avoid any confusion later on. So now it's actually very easy. I just assign probe Y to input Y and probe X to input X. And then I have the ability to already here define the configuration of the probe. So this is either pair or mono, the rotation of the shaft, and also the angle at which they are positioned. Actually, for angle and position, I would suggest doing it in the setup. But before we go there, let's take a minute to explain also the DC gap a little bit. So the proximity probes, they are very sensitive to the mounting distance to the surface that they are measuring. So it's very unlikely that you will be able to mount them at exactly their zero position. This means that at the normal mounting place, they will already read the value. And this is the DC gap. So this is the value that's there even when machine is not turning. So we have the ability to just easily measure it here with the button, or we have the ability to define it later on in the setup. So I'm not sure whether the probes here are even going to serve as a good input to measure the DC. So most likely I will need to stop the measurement and then go into setup to either input it manually or just leave it at zero. So after I've opened the setup, this is now what we call the bearing setup. So here we have all of the settings that are in regards to probe position, direction of rotation, etc. So first I have the ability to define the bearing name. So to make it easier for me to know, let's call this one bearing 1. I will just leave the default value, because in any case we just have a single bearing today. And then I have most of the settings that are outside, actually all of them, together with additional settings. So why I suggested to use setup instead of configuring them already outside is because you have here a nice graphical representation of what the system is actually asking you for. So if I am looking at the shafts end, I have the ability to easily define the Y position. I can choose to count from zero angle in left or right direction. So for our case, this is left at 45 degrees, meaning here. And then the second probe is right at 45 degrees, meaning here. The Tahoe angle is at exactly zero. So I would say fairly often these probes are mounted at exactly 90-degree angle. However, I need to stress out that our software actually covers any angle of the position of the probes, and it compensates for the phase between them. So it's not necessarily to only have the probes at exactly 90 degrees. Okay, if we move onwards to the settings, we have a checkbox here that is called calculate the subsynchronous orbit. So subsynchronous orbit is an orbit that goes between the first fundamental frequency and lower. So actually by this, I can capture any fluid-induced instabilities, such as the whirl and whip, and as such is a very useful analysis tool for the wholesome picture of the operation of your rotating machinery. It's easy to switch it on, just use the checkbox and then the channel will be automatically created. Okay, and then moving onwards to the shaft settings. So here I have the ability to define clockwise or counterclockwise rotation. Depending on these settings, you will see later on in the measure mode, you will get also a graphical representation on the orbit plot with an arrow showing the direction of rotation. And then the position, this corresponds to how the bearing is mounted. So if the bearing is mounted right side up, then the position will normally be bottom. If it's upside down, then we need to select top, because upside down actually means the bottom is now the top. Okay, the clearance circle, this is used to represent on the orbit plot the room that is inside the fluid or air bearing. So this is typically just copied from the technical drawings of the machine. Often it's defined with the two different diameters, so then we have the ability to define a slight ellipse, or we can do a circle. So the radius today is defined in the circle because I did not get two diameter information. And then we only have two more settings left here. So one is the average orbit. So the average orbit is calculated from the row orbit. This will all be shown in the measure mode. What needs to be known here is that average orbit essentially averages a couple of periods of data from row orbits into one data. And also we can show more than just one period when it comes to average orbit. So showing maybe two periods would mean that I will now have a history of two revolutions on my displays, not just one. And then selecting two averages means that for those two periods, for each period, we use two revolutions to average them into one set of data. The DC gap. Why is manual input important? Often the companies, they have the DC gap value already measured. So instead of measuring, this is crucial, especially for power plant turbines, because they are very rarely stopped. So you need to have a machine at a complete stop to measure the DC gap. So instead, often they will tell you the value and you can just manually enter it here. Okay, last but not least, the runout correction. So again, I would much rather show this in action in the measure mode. We will come back to here. But briefly, the idea is to have a separate measurement screen where you can evaluate the runout compensation or correction, depending how you're used to calling it. And then the values will be automatically input here, and they can be also stored in the setup. Okay, so now we can move to the measurement mode. Immediately after going into measure, you can see there is a predefined screen with a set of widgets already there. I will systematically go over them and explain which one normally represents what and which channels can be shown there. So first is the orbit plot. So this is a dedicated widget to orbit analysis module. Means that if you don't buy the orbit analysis license, you will not have the orbit plot widget. And then another widget of same nature is the polar plot. So those are both dedicated to the orbit analysis and are not otherwise available in Dewesoft. So if I focus on the orbit plot first, you can see that I am already showing the raw orbit channel on the orbit plot. So here I have the ability to show it in absolute mode, which means 0 is always at the center. So this gives me a nice idea of how far from the center the shaft is moving. And if I want to take a closer look at the shape of the orbit to maybe conclude some of the unwanted behavior such as rub and so on from the movement, then I can choose to have it scaled relatively. Relative means auto scale as per the maximum size of the orbit, both in X and Y direction. So before I mentioned that depending on where you put the Y and X probe in the settings, you will also have the graphical representation on the orbit plot together with the arrow of rotation. So of course Y shows the location of the Y probe, X for X, T actually shows the position of the tacho or key phaser, and the arrow shows that the shaft is rotating in clockwise direction. So I will need to go to channel setup and back to measure a couple of times because the replay file is speeded up twice. So actually it allows me to get data faster, but this also means that the whole run is finished sooner. Okay, so what needs to be maybe said here in regards to the orbit plot is also that we have the ability to show history in revolution. So for example, if I input 8 here, then I will get 8 revolutions. Maybe 8 is a bit too high because it creates a messy graph, but maybe 4 would have been a more natural value. So this way I can also see the movement of the orbit in those 4 revolutions. Or I can, of course, show just 1 revolution. Then we have another orbit plot on the predefined screen. So you can see that there is a couple of dots with RPM values. So this channel is called the shaft center line. You can see that we have a dedicated run up and coast down shaft center line. So actually the machine is just going into coast down mode. So I switched in the user input the direction to coast down, and then I will select a different color for the coast down shaft center line. So now we will be able to compare how the shaft center line moved during the run up and during the coast down. So the center line itself does not tell me that much. So I have the ability to easily switch on the clearance circle. So this is according to the diameter that I defined in the setup. So now I can see how the shaft moved in regards to the clearance that it has in the fluid or air bearing. And then it's fairly easy to create industry typical displays. So this actually is already one of the typical displays. It's called shaft center line with clearance circle. And then we can easily define from this a full motion graph. So let's start the replay one more time to get data. And I will show you how to transform the shaft center line with clearance circle into a full motion graph. Full motion graph is an important type of display. So it actually shows the raw orbit together with the shaft center line. So now I will change the color also for the run-up, so we will be able to see. And now actually we can see in the same graph the shape of the orbit and the movement of the shaft center line in regards to the RPM. All right, moving on. There is a couple of 2D graphs already defined on the predefined display. So what can I show on the 2D graph? A very orbit typical output to show is a so-called body plot. So this can be, for example, magnitude versus the speed of the machine for each probe separately. So let's change the color also here that we will be able to clearly see one and the other. And then I have the ability to show different things besides magnitude. So I can also show phase in either degrees or radians. So this is now minus plus 180. Or I can show it in 0 to 360, or I can choose to show only the real or imaginary part. On the 2D graph, there is another output that we can show from the orbit, and this is the average orbit. So the average orbit can also be shown on the orbit plot. So if I assign the average orbit here, you will be able to see that the shape is smoothed out in comparison to the raw orbit. That's because we are now averaging more than one period of data. And I chose to show 2 periods in my average orbit output. So now I am showing 2 revolutions at the same time. And also on the 2D graph, I show now 2 revolutions. Let's see what happens if I define under the average orbit to use more than just 2 periods. So let's say I want to use 4 periods. And we will go back to measure to see what kind of effect it had on both the 2D graph and the orbit plot. So now you can clearly see that the 2D graph shows 4 revolutions, not 2 anymore, and also the orbit plot now has 4 revolutions of history for the average orbit. All right, and then last but not least, the polar plot. So the polar plot is a very important type of widget for orbit analysis because it contains a lot of data in the single display. Actually, it contains both amplitude, phase, center line position, and RPM in the same graph. Again, same as with the shaft center line, because actually it has the center line data in here. The system will need the user to toggle between different states. So this is typically either done manually or it can be connected to one of the outputs on their logical controllers, for example, so that this can be done automatically. So now the machine is in Coastdown mode. I will also switch the color of the Coastdown to, let's say, orange, so that again on the polar plot you are able to see the different shape the shaft takes during the run-up and during the Coastdown. Last but not least, I've mentioned before the harmonic orbit. So actually, typically this is called the filtered orbit or annex orbit. Harmonic orbit is maybe easier for us Dewesoft users to understand because it's closer to the order tracking. But actually in the most recent version, we've changed the naming to 1x, 2x, and so on orbit to be in line with what the industry typically uses. So let's show on the orbit plot different harmonics. So I've selected to extract the first 4 harmonics, and I can show them all in the same graph. So for most of the stuff that I've shown today, we support either multi-trace. This means that more than one quantity is shown on the same graph, or multi-graph mode. So this means every output on its own graph. This might be important because some of the competition, they stress this out, and it's good to know the terms so that we can immediately confirm, yes, we can do also multi-trace and multi-graph representation. So these are now the harmonic orbits from 1 to 4 shown on the same orbit display. Okay, also kind of self-explanatory, we have a digital display with an output of speed. So that was the predefined display. Of course, it can be modified, and this is just a sort of easy to use first display. Most often, of course, the customer will customize them. Okay, let's now check the runout compensation and how it's done. So I've inputted in the setting to use 2000 RPMs as a runout compensation, and now I've opened a dedicated runout compensation screen. So I have here the ability to check the RPMs as well, so that I will know once the speed is suitable for me to perform the compensation, and the system tells me the status is ready. And here I have also 2 time domain datas from both of the probes. So we are approaching the 2000 RPM. I will click start, and the system told me in progress, and now it says done. So let's see what happens if I now reopen the runout compensation in the setup. So now the software automatically filled in the data for the compensation. And this means if I click OK and save this in the setup, I will now reopen the same setup. You will see that the values are here. So this means that you can only do this one for the particular machine and then just reuse the setup. No need to measure it again. Another thing with a similar approach is the reference orbit. So over the years, we've received quite a few requests to be able to show historical data to the current measurement data. So this is especially a powerful feature that Bentley, Nevada, for example, has, and they're proud on that. So we wanted to do something along those lines and to be able to offer the customers something like this. So the flow here is a little bit different. So we start the reference orbit measurement. It takes as many averages as we defined in the software, in the setup, and then it says copy to clipboard. This means that now I have the data for the reference orbit in my clipboard. So I've just opened the notepad and I've pasted this. And now if I want to upload this back to the Dewesoft software, I will just save this. Okay, let's call it Runout demo into a text file. Okay, and then if I go back to my channel setup, open setup here, and now you see that I have the ability to also select reference orbit. I will say import, select Runout demo, and the data is imported. So now if I select OK, when going back to measure and going to the normal predefined display, let's remove the orbit. Now I have the ability to also show a reference orbit. So I've taken 10 revolutions, which means that it's a bit messy to look, but this can be, of course, defined to a lower number. The main idea is now I will be able to overlay the previous measurement with this one with as little work as possible. And to conclude the demo, let's take a look at the waterfalls. So here I've added 4 3D displays to a different measurement screen, and now I will just assign the order FFT, for example, to the first one, from the Y probe, and then from the X probe to the second one. We will lower maybe the axis value a little bit to see the orders better. And then I can also assign time FFT, of course lower the frequency here because it's auto-scaled as per the sample rate that I've used. Okay, 500 I think should be enough. So then I have the ability to check also the waterfalls. So this is, I would say, fairly similar to the order tracking configuration. Okay, so this I think concludes a brief overview of what we can do in terms of what we can measure and what we can show in our software. And let's return now to the presentation to take a look at the conclusions. All right, so one important conclusion, actually this is a pre-conclusion because there is another slide for conclusions later on. A pre-conclusion would be that what differentiates us from other providers is that we can easily combine orbit analysis with other modules. So of course, we will focus on this later on in the sales section a little bit more, but I wanted to touch it already here because it's fairly important. So as with most of the other measurements we do, especially when it comes to vibration, noise, etc., we are focusing strongly on the R&D users. So for R&D purposes, it's crucial to be able to use more than just one analysis in the same system. So this way we can offer easy simultaneous measurements of orbit analysis, order tracking together with FFT. Actually, we have a dedicated package for this, a little bit more on that in the next section as well. So Orbit Analyzer would be a very nice tool for R&D of rotating machinery. And the laptop battery just died. Hi, welcome back. Before the short break, we've done an intro into the conclusions. So we've mentioned that besides orbit analysis, we also offer a dedicated orbit analyzer package. And then there are other actually numerous configurations possible. So here I only listed a few that might be, let's say, main and especially useful. So one is to combine orbit analysis with power module. So this comes in handy with analysis of power generation in power plants. You can then cover both the electrical side and the turbo rotating machinery side. Another interesting combination would be orbit analysis plus rotating machinery analyzer. This essentially also brings balancer to the package. And then another interesting combination might be to combine orbit with our sound modules and to perform a complete vibration and noise analysis. So to list a few short conclusions, one thing is we offer a complete analysis for orbit measurements, including display widgets. Our software is very easy to use. We do synchronized acquisition of multiple sources and multiple analysis modules. So actually, according to the feedback we've received from the industry, we are the only provider in the world that does orbit analysis together with order tracking and torsional vibration, for example, and all in the single software. A very good thing to know is we do, of course, flexible hardware configuration. This means that we can offer the customer to have the hardware and connect exactly the transducers that they might already have, or to use the sensors they would like to have in the complete setup. And an important thing to point out is the multi-probe support. So with our LV module, we can directly connect most of the proximity probes on the market. And this allows the customers that might have competition software to just change the data acquisition side and not the probes as well.